Hello, this is the third video on circular motion. So we are familiar with the Cartesian plane, and this is called our frame of reference, and we can position anything on the Cartesian plane, say here, and that as a position x1 and y1, and we can write the coordinates x1, y1. Now, when we have something spinning around a central point, these coordinates are going to change very fast, and the Cartesian system becomes quite cumbersome. So we need a different frame of reference and coordinate system. So often with circular motion we use polar coordinates, and we change the so we define a position with its length from the origin and its anti-clockwise angle. So for example, the position here is going to be r theta. So this could, if r is 1, that would be 1, and I'm going to say that this is, let's call it 45 degrees. So we define a full revolution as 2 pi, half a revolution, so that's full, half a revolution as pi, pi over 2 is a quarter of a revolution, and pi over 4 is going to be the angle that we have here. So we can write that as 1 pi over 4. The polar coordinate system is really good at measuring position, velocity and acceleration in circular motion. It's much more powerful than the Cartesian system. So here I've put a transfer system to map Cartesian coordinates onto polar coordinates. So I'm going to keep that there, and I'm going to keep my Cartesian coordinates. So we define in this positive is positive y, and I'm going to draw my orbit, and I'm going to say this is position 1, and it moves to position 2. We're going to have an angle, and that is a function of t. We say that's positive, and it's going to move in this direction. Now I'm going to introduce my polar coordinates. Okay, so now I'll go into more depth about this in the second video. So I'm going to define this direction as r hat t. Now, if a vector has a hat on it, that means it's a unit vector. and we calculate the unit vector by dividing by the magnitude. Okay, so I'm going to have my angle theta here. And here. Okay, so I need to name this side, this side, this side, and this side. So this is just simply cos theta using the conversion. This is sine theta. This is cos theta. And this is negative sine theta because we're going in the opposite direction. So this is a common misconception. This is negative because it's going in this direction. So this is something that often confuses a lot of people. If we have a person looking at this and it's going, this is called the angular velocity, and that is the change in the angle with respect to time. So if the angular velocity is positive, we have anti-clockwise motions. If it's negative, we have clockwise motions. And if it's 0, it's stationary. Now let's change our position, and the person is looking in this direction. These reverse, so the angular velocity is dependent on the position of the observer. That's why it's really important to have a frame of reference from the origin. Now, angular velocity is a vector. It has magnitude and position, but for this reason it's sometimes referred to as a pseudo vector. Another misconception is that position, let's not use position, is that radius 1 is equal to radius 2, and let's say angle 1 from this position going over to this position is equal to angle 2. Now the magnitudes of the vector will be equal, but don't forget a vector has magnitude and direction. So if I'm over here, I'm going to call this theta hat, and I'll go over that. The coordinate system, our frame of reference, stays the same, but theta hat is pointing downwards and r hat is tangential to theta hat. For two vectors to be the same, the magnitude and direction needs to be the same, both of them. Having just the magnitude the same does not mean that the vectors are equal. So let's have a quick look at the domain. So let's see something's going from this position all the way over to this position. So from position 1 to position 2. So our theta goes from 0 to 2 pi. So those are the possible values for theta. Say for instance, this is the ground and we swing in a particle on a piece of string. So I suppose we better do the domain for the... So it must be greater than 0, otherwise we just have a point. And I suppose r can go all the way to infinity. A final note on, let's say, change in theta with respect to t. And let's move to the usual I've forgotten the notation name. Let's go dt. Yeah, so Newton uses this notation, I think, and I've forgotten what this is called. Okay, so let's move from change to d for differentiation. I think that's everything I wanted to go over in this video.